In this video, we'll continue our discussion of inequalities by learning to solve inequalities in an algebraic way. So up to this point in the past few videos, we haven't had to do a lot of paper and pencil math, and that's going to change here. The good thing is that everything that you've learned so far about solving equations is going to apply to solving inequalities, with one exception. And so I have a note here, procedure for solving inequalities. You may use the same procedures to solve inequalities that you use to solve equations, except, this is the only difference, that the direction of the inequality is reversed if you multiply or divide both sides by a negative number. So what does this mean? In the course of solving an inequality, if you come to a point where you have to multiply or divide both sides by a negative number, then you have to remember to reverse the direction of the inequality. And we'll see some examples of that later on in this video. But first, let's just take a look at a simple example applying the procedures for solving equations to solving an inequality. So we begin with 3x plus 7 is greater than or equal to 13. If I were solving an equation, I'd subtract 7 from both sides. Then I would be left with 3x is greater than or equal to 6. Divide both sides by 3. Again, not a negative number, so nothing out of the ordinary here. And I would end up with x is greater than or equal to 2. Well, what does this mean? What that means is that I can substitute into the original inequality any value for x that is greater than or equal to 2, and I will end up with a true statement. If I substituted any value that was not greater than or equal to, in other words, was less than 2, I would end up with a statement that is false. So when we substitute a value and get a true statement, that value is called a solution to the inequality. And remember, because we want any number that's greater than or equal to 2, there are an infinite number of possible solutions. There are also an infinite number of not possible solutions. So what I'd like to do is show an example here of how we can check to make sure that we got the right answer. So I will check 3 different values. Number 1, we'll check a value greater than 2. Second, we'll check x equals 2. And then we'll check a value that's less than 2 to see what happens when we substitute those values into the original inequality. So let's pick a value greater than 2. So how about 5? Well, when I substitute 5 for x, multiply by 3, and add 7, do I get a value that's greater than or equal to 13? 5 times 3 is 15, plus 7, that's 22, and that is indeed greater than or equal to 13. And so we can see that 5 is part of the solution set to the inequality. 3x plus 7 must be greater than or equal to 13. Now, we tried a number greater than 2. Let's try 2 itself. So when I substitute 2 for x, I get 3 times 2 plus 7. Is that greater than or equal to 13? I get 6 plus 7, and that is 13. Is 13 greater than or equal to 13? It just has to be either or, and it is equal to 13. So 2 is also a solution to that original inequality. Now let's try a number that's less than 2. How about 0? So when I substitute 0 for x, I get 3 times 0 plus 7. And I want to know, is that greater than or equal to 13? 3 times 0 is 0, plus 7 is 7, greater than or equal to 13? And the answer is no. So therefore, 0 is not a solution to the original inequality. And the same would hold true for any number that's less than 2. 0, -5, -237, etc. So we're not going to have the time to check each one of our solution sets in this video, but I wanted to show you how that works so that you can do that. You can replicate this process and do that for yourself. It takes a little bit more time, but the good thing is that you'll build confidence knowing that you have the right solution to the inequality. All right, so let's talk about graphing now. I start with my number line, and I want to graphically represent all the numbers that are greater than or equal to 2. Since I have the little equal sign underneath the greater than, I do want to include 2 in my solution set, and so I'm going to use a closed circle at 2, shade in the direction of the inequality, which is to the right, and so that is the solution set. That is a graphical representation of all of the numbers that I could plug into the original inequality and end up with a true statement. All right, so here's one for you to try. Please pause the video, work through the steps yourself, even check your answer, and then turn the video back on or come back to the video and check to see whether you've done this correctly. Okay, ready? We have 8x minus 2 is less than 3. Going to add 2 to both sides. We end up with 8x is less than 5. Dividing both sides by 8, we have x is less than 5/8. I'm not going to go through the checking the 3 different cases here, but you could check a number greater than 5/8, 5/8 itself, and a number less than 5/8, and you will find that any number that you plug in that's less than 5/8 will make a true statement. Anything else will not. And to check, you don't have to use fractions. You can, any number less than 5/8, plug in 0. That's a convenient number. You can see that 8 times 0 is 0, minus 2 is -2, and -2 is less than 3. So we won't do that here, but let's go ahead and graph our solution here. So we start with our number line. Since 5/8, there's no equal sign here, 5/8 is not included in the solution set, so we want an open circle at 5/8. We graph in the direction of the inequality, which is to the left, and so that is the graphical representation of all of the possible solutions to the inequality 8x minus 2 is less than 3. Let's go on. So what we have here now in example 6 is an example that is going to require us to multiply or divide both sides by a negative number. And so we want to illustrate how to deal with that here. So I begin with 5 minus 3x is greater than 7. I'm going to leave the x on the left side, which is the way we'd like to end up anyway, and I subtract 5 from both sides. And when I do, I end up with negative 3x is greater than 2. To isolate the x, I would have to divide both sides by negative 3x. And here is the instance where I have multiplied or divided both sides by a negative number, and so I'm going to have to remember to reverse the direction of the inequality. That means I'm either going to change a greater than to a less than, or less than to a greater than. And I end up with 2 over negative 3 is the same as negative 2 over 3. So that would be the solution to this inequality. Now, some people may not understand why or how we can just say change the direction of the inequality. So in this particular instance, before we look at graphing, I am going to work through a different type of solution to this, and you're free to use either way, whichever way is most comfortable or makes most sense to you. in the future. I will always, and I will explain why, we'll use this method that we just used, what I'll call the blue method here. So let's say in the green method, we start again with 5 minus 3x is greater than 7. This time, instead of leaving the negative value for x, the x term on the left side, I'm going to add 3x to both sides. And when I do, I end up with 5 on the right, greater than. Now, it doesn't matter because addition is commutative. It doesn't matter whether I add 7 plus 3x or 3x plus 7. That's like saying 2 plus 3 is 5, 3 plus 2 is 5. It doesn't matter which way I do this. In general, I'm going to put my x term first, but you can do it either way. Then I'm going to subtract 7 on both sides. When I do, I end up with negative 2 is greater than 3x. This time I divide not by a negative number, but by a positive number, and I end up with negative 2/3 is greater than x. But you recall that we like to have the x value on the left side because it's easier for us to understand x has to be less than something or greater than something or greater than or equal to something, etc. The way we have to do that is we're going to read the inequality from right to left. When we do that, we read x is less than negative 2/3. We write it the way that we read it, x is less than negative 2/3. And you can see that we ended up without having to reverse the direction of the inequality. We just wrote it in the order that we read it from right to left, and we ended up with the same answer. So you can see that the blue method is actually shorter, involves less steps, and so that is the preferable method. But if the green method makes more sense to you and you'd like to do that, then you're welcome to use that strategy as well. Let's go on to graph this then. So we have our number line. We have our negative 2/3. Now, even though the original inequality had a greater than symbol, our solution set is actually has a less than symbol. We don't include negative 2/3, and so we need an open circle at negative 2/3, and then we shade in the direction of the inequality, which is to the left. Remember, don't shade in the direction of the original inequality. We shade in the direction of our solution set, which is x is less than negative 2/3. All right, so let's let you try one of these on your own. You have 4 minus 5x is greater than 7. If you get stuck, you can go back and look at the previous example. Whether you use the blue method or the green method is not important. Pause the video. When you restart, I will use the blue method to solve this. Okay, are you ready? We have 4 minus 5x is greater than 7. This time, I'm going to leave the variable on the left, subtract 4 from both sides. When I do, I end up with negative 5x is greater than 3. Dividing both sides by a negative number, by negative 5, I have to remember to reverse the direction of the inequality. When I do, I end up with x is less than negative 3/5. So what we did here is when we, in the course of solving our inequality, we multiply or divide both sides by a negative number, we're going to reverse the direction of the inequality. Now let's go ahead and graph this. We have our number line. Since negative 3/5, there's no equal sign, so negative 3/5 is not included in the solution. So we're going to start with an open circle at negative 3/5, shade in the direction of our final inequality. Again, the original one was pointing to the right. This one is pointing to the final solution, points to the left. So we shade to the left, and that is our solution to 4 minus 5x is greater than 7. Any number in the shaded region substituted for x will yield a true statement. Any other number will yield a false statement. So that's going to do it for these basic examples of solving inequalities. We'll look at some more complicated examples coming up.